recording. Okay. So, this is where we left off in the lecture last time. And so this is the names for naming branched chain alkanes. Step 3 was number the carbons of your parent chain, starting at the end that's nearest to the substituent. So your substituents, the things that are substituting hydrogens on your parent chain, get the lowest number. That's that same rule I had used to get 1 for the double bond and then 3 for the alcohol, right? Number 4 then is assign a number to each substituent based on its location, listing the substituent in alphabetical order at the beginning of the name, that's the prefix. You separate the number and words in the name by dashes. So anytime there's a number that's going to separate from a word, it's always dash, okay? So word, number, word would be word, dash, number, dash, word, right? Okay. All right. So if more than one of the same type of substituent is present in the compound, I'm going to indicate this by using Greek prefixes. You'll recognize these Greek prefixes. They are di, tri, and tetra. You'll ignore these prefixes when alphabetizing for the order that you put these substituents in for that prefix naming. Okay? So for example, if we had an ethyl and a methyl, the ethyl is going to go first. Doesn't matter how many of them there are. It could be tetraethyl. Doesn't matter. Okay? It's not going to change the order. Okay. And so right here we actually have the nomenclature with pictures. You're going to notice all the nomenclatures for these always use pictures to define them because that is the most direct methodology, right? This book would be so much longer if it was written out in words completely. Every single one of these. It would be wild. Okay, so this right here is methyl. That's 1 carbon, right? Ethyl, that's 2 carbons. Notice the little break over here. That's because these are chains. They're coming off the side. They are branches off the parent. Okay? And so this would be a propyl group. Anybody ever heard of isopropyl alcohol? Rubbing alcohol? Okay, that's isopropyl alcohol. This is the isopropyl group. See how it's actually the middle carbon that's attached right here? It would make a little V. See that little V? Okay. So that's the iso prefixes that makes that V shape. Okay? At the end is like a tail, like a fish tail. All right? And isopropyl alcohol is isopropyl alcohol because it is an isopropyl, and then over here there's an OH, which is an alcohol. And that's why that's named that way. So is everybody okay with reading the line structures and condensed structures here? Okay. Mm-hmm.
So that line structure, that weird little thing is just OH. Like it's an alcohol.
In isopropyl alcohol.
Okay.
Yeah. This over here could be anything.
Okay.
Yeah. This is our R group. I don't know why your book decided not to use R group. I just took the pictures from your book because they'd be familiar to you. And that way you don't have new terminology added and you go, wait. Okay, but yeah, this could be anything. Most commonly this is going to be a parent chain. So this could be like an octane over here. Okay. But yes, the old naming methodology, isopropyl alcohol, that's an alcohol there. You could have like isopropyl chloride. That'd be a chloride over there. Okay, haloalkanes. So halogens are going to be common substituents on alkane chains. They're going to be referred to as haloalkanes. They're somewhat of a special group because halogens only make 1 bond, right? And so they're very analogous to hydrogens actually because they only make 1 bond. They don't do anything else structurally to it. And they're kind of just direct substituents for hydrogen, aren't they? They don't make any extra bonds. They don't do anything else. Cool. The rules for naming the haloalkanes are going to be the same as those for naming the branched alkanes, with the halogen being the substituent. And so we're just going to directly tack on a bromo, chloro, iodo, a fluoro. And that's going to be our prefix. Wherever those are located, that's going to be our numbering. So let's go ahead and talk about cycloalkanes. So the rules for determining IUPAC namings for the cycloalkanes are going to be the same as those for the branch chain alkanes. There's going to be a very small amount of modification. Your ring is going to serve as the parent name as long as it has more carbons than any other substituent. Okay? Now keep in mind that this can have substituents off of it. You're going to number those carbons just in that ring. Okay? Okay. You're then going to identify the substituents that are off of this ring. You're going to number the carbons in the ring. Carbon number 1 will always have the substituent because that's always going to be the first spot. Kind of like saying, where's the origin of a sphere? Wherever you want it, right? Really wherever there's something unique, right? Remember, this is circular, so wherever something unique is, that's the origin. Number 1 spot. All right, so you're going to assign numbers to the substituents. On a ring that bears a single substituent, you don't actually have to put the 1 because it's implied. Wherever that substituent happens to be, that is 1, isn't it? Okay? If you have more than one substituent, then you're going to have to number them off. Starting on one of the substituents that has the highest priority, that's the most important to you, you would then number from that to give the lowest possible number to everything else. All right, so organic compounds with the same number of carbon atoms can have carbons connected in many, many different ways. In fact, remember where we were talking about the octane rating and I showed you what the octane they're referring to there is? Did you notice that it isn't actually named octane? Like it was not a straight chain with 8 carbons in it? That just wasn't, was it? Yeah. And this is why we have to have this fairly complex naming, because we have to be able to figure out which one of these compounds it is. Okay? So, molecules with the same molecular formula but different connectivity or arrangements, these are called isomers. The name is actually taken from the Greek iso. You may remember isotopes. Remember that? Isotopes was like carbon 13, right? Same element, different mass, right? In this case, we're going to be isomers. So iso meaning same, meros meaning part. And so this is going to be where we have the same formula for the compounds, but we're going to get different structures. Okay. All right, so let's go ahead and look at some structural or conformational isomers. When an organic compound has 4 or more carbons, the carbons can connect in more than one way, and this can give you very different structural isomers. So when 2 molecules have the same molecular formula, see these are both C4H10, right? We can have wildly different connectivity, how they're actually put together. Okay? Kind of like if you buy a Lego kit, can you only ever make one thing with it? Nope, you don't have to follow the directions, do you? Even if you follow the directions, sometimes it turns out different. Okay, and so molecules are the same thing, right? If we have the same parts, we can actually arrange them in different ways. This can give wildly different properties. Okay? Very, very different properties in what it does, especially in biological systems. All right. And so this right here is just the straight chain alkane. Everybody see that? 4 carbons, one after another, straight chain. This is that branch chain that I was talking about. See here we would have a parent, and then we have a branch coming off, don't we? Okay. All right, so because of these connectivity of the carbons is the same, there's 2 representations of the same molecule right here. These are not actually different, are they? Can everybody see that really a carbon chain is like a chain, isn't it? So when we looked at these carbon chains, we write these stretched out like you would like show a chain to somebody, right? So you stretch the chain out. Ooh, ah, looks nice, doesn't it? Okay, and you can count the lengths. Cool. But when you throw a chain into a bin, is it going to be stretched out and nicely arranged? When a chain's actually being used and things are happening to it? No. No, it usually is not, right? It's usually folded in. The shape can change. And so we need to be careful about defining these things. These are actually the exact same structure. It doesn't matter which direction the carbons are pointed. That doesn't matter. It doesn't matter if we flip it. So we start at the right or the left. When we're actually talking about molecules, they don't have a right or left. They just rotate all over and bounce around everywhere, don't they? Okay? And so the same thing happens with the chain. It twists, it turns, it morphs. Okay? And so when we look at these are the exact same molecules. There's nothing different at all. The same. Okay? The type of isomer that is different is going to be the conformational isomer or conformer, where they have a slightly different orientation, but they're the same molecule. And if you provide this energy, this is just going to rotate over to that, isn't it? Okay? And so that's what we refer to it. Typically, we refer to this as just conformer because chemists are a little lazy. But you can also refer to it as conformational isomer. Okay? So it is where you've twisted them. It is a temporary change, not a permanent change. This, for example, structural isomer, this is a permanent change. These are never going to be the same thing, are they? Yeah, you'd have to react them, break them apart, wouldn't you? Okay. Okay. Can everybody sort of see that? Right. One of the easiest ways to adapt this into your head is thinking of chains or wires. Okay? So like your charging cord. If I wanted to make a double-ended charging cord, I actually have to cut my charging cord up, don't I? Okay? I can't just twist it into whatever shape I want there, and it'll make that. This would be my charging cord being rearranged so it's not putting so much stress on my hand, right? Okay? I could have it nice and straight if I wanted to reach, right? But I might loop it so it's not pulling on me, right? Okay. And that's going to be conformational changes. Okay, so let's talk about this isomerism in organic compounds a bit more. We start right here. Do the molecules have the same molecular formula? If that's a no, then they're just not isomers. They're not related. Okay? You could have a C4 versus a C5, right? You have a different number of carbons. They're just different compounds. Okay? If they do have the same molecular formula, then you'd go down here. Do the molecules have the same name? So if they have the same name in the IUPAC naming, then they're going to actually be conformational isomers because they look different because they're twisted different, but they have the same connectivity. Okay? If they don't have the same name, if you would actually name them differently in the IUPAC naming, then they're going to be structural isomers. They actually have different connectivity. They're joined differently. Okay, so let's talk a bit more about some more isomers. Notice these actually are connected in the exact same way, aren't they? Can you see that? Yeah, look at that. Carbon's right here, carbon's right here, isn't it? Same thing. Okay, so in terms of structural isomers, these are actually the same isomer in terms of structural isomers. Okay? If you were to try to give these two compounds as medicine, you would have wildly different effects depending on which one you gave. Okay? And so what these are is this is the cis-trans. These are called stereoisomers. Do you guys know why stereos are called stereos? Does anybody know what stereo is? That word? Okay. Okay. It means a different three-dimensional orientation. Okay? So a stereo is called a stereo because it has more than one speaker. And so you can hear sound differently from each ear, right? And it gives you a sense of perspective and orientation. Okay? You ever been to the theater where they do that? Where it sounds like somebody's walking up behind you? Yeah. Yeah, that's called stereo sound, right? Okay. All right, so this is going to be stereoisomers. So they're going to have slightly different three-dimensional orientations. And in this case, what they're going to be defined as is cis is where we have them on the same side, So see how these CH3s would be on the same side, pointing in the same direction, right? This one right here would be called trans, and it's where they're going to be on different sides of the structure, okay? And so cis, same, trans, same, all right? I'm sure you've all heard that terminology used before, okay? Cis being same, trans being opposites, right? Okay. Okay, notice that again, it's not actually possible to rotate to get one to the other. Can you see how that's not possible to rotate? Because we have two connections, right? Okay. The easiest way to sort of understand this is actually take your fingers, connect it in two places. You can then move those back and forth. So this would be like a double bond. This would be like a ring, right? We have our thumbs on opposite sides. That's trans, isn't it? If we try to rotate to the other, what happens? Yeah, we can't actually rotate it without breaking our connections, can we? Yeah, so we would have to break our double or ring structure, wouldn't we? Okay. If they only have one connection, notice I can freely rotate around, can't I? That would be confirmation. Okay. Honestly, you'll learn it a lot better if you go ahead and take your fingers and actually play with it three-dimensionally. Yeah, you can only learn so much by just looking at pictures. Okay. All right, so because of that restricted rotation on your carbon-carbon bonds and things like cycloalkanes or double bonds, we actually end up having stereoisomers generated depending on which side our substituents are on. And so that same attachment to the carbon skeleton can have different spatial arrangements. These are going to be called stereoisomers. You okay?
Oh, yeah, we're close tomorrow.
Oh, okay. Okay. Well, that's good news for me, too, because I really needed to catch up. All right. So, again, those are stereoisomers, different arrangements in three-dimensional space, right? Okay. Okay, so this right here is, again, that cyclopentane. They're going to be one of the class of stereoisomers. This class of stereoisomers is typically referred to by most people as cis-trans isomers. There is a more advanced language that can be used to describe more complicated situations with this, but this is plenty for all of you, okay? Has anybody ever heard of cis or trans fatty acids? Guess what that is? Yeah, it's a double bond. In a cis fatty acid, your chain kinks like this. In a trans fatty acid, your chain is going to kink like this. Okay? So it's just the same thing. That's what it always meant. Okay. Anybody have any questions of that so far? Right. One of the easy ways to remember this, if you don't already remember the cis-trans dichotomy, is that cis on the same side, right? Trans across, like transatlantic, right? Okay. All right, so cis-trans isomerism actually occurs more in alkenes than any other thing. That's probably the majority of the ones you're going to see, but it also occurs in any ring situation as well. Okay. Because again, double bonds are not going to allow rotation around the double bond because you'd have to break part of the double bond. Okay. So the organic chemists, we're going to say that carbon-carbon double bond has a rigid or restricted rotation. The compound with similar groups on the same side of the double bond. This is a cis stereoisomer. Compounds with similar groups on opposite sides of the double bond. This is going to be our trans stereoisomer. This language can get a little bit loosey-goosey, but you're always trying to identify what the sort of higher priority, what you're actually looking at as interesting groups, okay? As being on the same side or opposite sides. So if one of the alkene carbons has two identical bonded groups bonded to it, then we can't really have cis-trans stereoisomers, can we? So for example, this right here is a double bond with cis isomer. This one's with trans isomer. What would happen though if instead of having a hydrogen here, we had another CH3? Is that cis or trans? So these are opposite, right? So that'd be trans, wouldn't it? These are same. That's cis, isn't it? so that's neither, right? Because it actually doesn't matter which side you be on. If you manage to flip these somehow, it wouldn't change anything, right? Okay. So if you end up doubling the group, that right there is actually going to get rid of your cis and trans isomerism. Okay? Okay. Anybody want to tell me what would that be called, having groups on the same carbon? You have two kids that come out of the same mother at the same time. What's that called? Twins? Anybody know what that's called in terms of Greek? Okay, I'm an Aquarius. Is there one of those that refers to twins? Gemini. Yeah, geminal. So it's geminal. Okay, it means it's on the same location. Okay, vicinal means it's next to each other, as in vicinity. You'll recognize all these roots are used in all the languages we speak. Yeah. Okay, so this is the unsaturated fatty acids. These are going to contain cis alkenes. This is the omega fatty acid. That's actually the symbol for omega there. And so that's the lowercase, by the way, in case you're wondering. These designations are commonly going to be used in nutritional literature. In this system, the carbon furthest away from the carboxylic acid is actually your first carbon. Okay, so you actually start counting at the end of your chain instead at the beginning. And what you then do is the next carbon is 2, the next one 3, so on. These can actually be given then, these Greek letters, in alphabetical order, as the Greek alphabet goes, to describe where that double bond is. Okay. And so the polyunsaturated fatty acids, these are going to be things like linoleic and alpha-linolenic, are beginning to be considered the essential fatty acids. Does anybody know why they'd be essential fatty acids? Anybody know why essential nutrients are essential?
Because your body doesn't naturally make them.
Got it. Got it. So these are all things that you can't naturally make. Okay? Or if you do have some sort of pathway to make them, it's not active. It's not something you can normally do. But yeah, you need them in your diet. Without them, you won't be able to get the compounds that are derived from them. So this right here, some different examples. This is actually how you go ahead and denote this. So this is the omega fatty acid right here. It's the 7th position, and so you mark it 7. Okay. This right here is actually the fatty acid that you probably associate with the taste of butter, by the way. That's that buttery taste, if you're wondering. This right here is olives and corn, oleic acid. Notice it's an omega-9 fatty acid. This right here is soybean, safflower, corn, this linoleic acid, commonly known as LA, i.e. the linolenic acid, and omega-6. You may have heard of omega-6 before. This is one of the main things you actually get from corn that's healthy. There's actually not a huge amount of healthy stuff in corn. But it has essential fatty acids, which is actually quite important. Okay, anybody have any questions on that stuff? All right. Can anybody tell me, is that cis or trans right there? Cis, you got it. Mm-hmm. On the same side, right? Trans would have been the opposite side. Okay. Now, the stereoisomers, this is chiral. Chiral actually means handedness. Okay. Did anybody remember when I talked about meth the other day? Meth is named after what? A methyl group. Okay. And it's actually that chirality of that methyl group that determines whether that is an active drug or not. So let's go ahead and look at limonene. So this is the citrusy scent that you probably associate with things like oranges, lemons, that sort of thing. Okay, that's why all the different citrus fruits kind of smell similar. Okay, that's actually limonene. And so this is the structure for that right down here. And notice this bond right here. This is going away from you, isn't it? See that bond? Okay. So this right here is actually the limonene from turpentine. Okay. Anybody ever used like paint thinner, chemicals like that, and went, that smells kind of citrusy? Yeah, that's why. Is because it actually has what would be the same compound, same molecular formula, same arrangement, everything, right? But instead of having a bond that goes out away from you, it actually comes out towards you. Okay? And so it has a different stereoisomer, doesn't it? It has a different three-dimensional arrangement. But this is not a cis-trans three-dimensional arrangement, is it? We don't have another group to compare here, do we? Yeah. Okay. So you can actually distinguish those, even when you're smelling, you can actually distinguish them. And those are actually what are called chiral molecules. Specifically, those are going to be enantiomers. So what they're going to be is identical molecules that are superimposable. So we can actually take, that are not superimposable, excuse me. So we can actually take this, and what we would see is if we took a mirror image of the first one, that would be this one over here, wouldn't it? That's like this one standing in front of the mirror, isn't it? But if we tried to superimpose them and make them go on top of each other, what we would see is it would actually look like our hands, right? Where their mirror image is, but I can't actually superimpose those, can I? They're not actually the same structure. Okay? And this is actually what chirality is named after. Chirality is actually named on the base word, which is chiral, which is handedness. That they're like our hands. Okay, so the compounds that are non-superimposable mirror images of each other, these are going to be referred to specifically as enantiomers. One type of enantiomer, probably the most important type, is chiral compounds. Okay. All right, so if we look at a pair of shoes, for example, they are non-superimposable mirror images. They have chirality, don't they? Okay, if you try to put your left shoe on your right foot, what happens? Don't work quite right, does it? Okay. Okay, so objects that are termed chiral, again, this is the handedness of it. Most enantiomers contain a chiral center. This is going to, more often than not, be a tetrahedral carbon atom. So a carbon in the middle there, that has 4 different groups bonded to it. That's actually the reason why our hands are chiral, because they have 5 different groups bonded to it, don't they? So chirality. Same thing with our toes on our feet, right? We have more than 4 groups bonded to the center, and so we're chiral. Okay? Can everybody see that with this one? That these are mirror images of each other, but non-superimposable, right? You can't just line them up and they merge. All right, so let's go ahead and look at how we identify chiral compounds. Step 1 is going to be locate the tetrahedral carbons. So carbons have 4 atoms that would be around them. Keep in mind, if you're given a line edge formula or a skeletal structure, the hydrogens won't be expressed. Okay? So tetrahedral carbons would have 3 things bonded to them, and then they would have 1 non-written in hydrogen, right? Okay. You're then going to take those tetrahedral carbons, you're going to inspect them, determine if the 4 groups that are attached to the tetrahedral carbons are actually different from each other. If you have 2 of the same group attached, it can never be chiral. Okay? Because no matter what you do, it's always going to be a mirror image that can then be superimposed to each other. Great example of an achiral item that you can't actually do chirality to is your chairs. If you took a mirror image of that, you could just superimpose it, right? It'd be the exact same, no difference. Okay? My glasses. Mirror image, right? That can be superimposed. I could fit it on my face even if I flipped the sides, couldn't I? Okay. So, step 3, assign the chiral centers. Typically what you do is you put asterisks where those chiral carbons would be, so you can denote, hey, that's a chiral center. That has chirality. So let's talk about some of the consequences for chirality. Biological molecules, such as those in your nose, these are handed. They're chiral molecules, can only fit into a complementary receptor. That's going to be one that accommodates that specific shape. That's true for almost all of your biological structures. All your biological structures, almost all your biological structures are chiral themselves. And so they only fit one chirality. Anybody heard of mirror life? Nobody's heard about that at all? It's recently been making its way out in the news. So there's a proposal. We're chiral creatures. We have orientations that are very, very consistent. Okay? We actually only have one type of orientation for most things in our body, including our DNA, everything. Okay? They've been working on synthesizing the opposite orientations for all these things. And so you could actually create a living organism that has the opposite orientation for everything. Okay? And it would react oppositely to every chiral compound. Right. People are terrified of it because there's absolutely no telling what it would do and how it would interact with normal organisms. Could mostly not interact at all. Could be completely poisonous on normally benign things. Okay? Could be just absolutely crazy. So in some cases, one enantiomer of a drug can actually be beneficial. In the other case, the other enantiomer of the drug is actually harmful and is poisonous. Okay? In pharmaceuticals, only a single enantiomer typically has biological activity. Usually the other enantiomer is either purified away or they just gave you what's called a racemic mixture, which is a mixture where you get both chiralities. Okay? Anybody ever bought any of the health supplement stuff from the stores? Anybody ever seen RS? No? Okay, so if you look at like an amino acid supplement, you can get the R form and the S form. That's the chirality of it. Okay? And one of those enantiomers actually is something your body can use. The other enantiomer, on the other hand, is waste. You just poop that out. Okay? So if you go to the health supplement stores, they'll sell you the really nice ones. Typically sell you only one enantiomer, so they can sell you smaller bottles. The bigger bottles that are cheaper typically are racemic mixtures, and so half of the bottle is just junk. You can't use it at all. Okay? That's why they sell you more for a lower price. Yeah. So you do have to watch that out. It's a pretty common trick that people play on you. Okay. So in the case of thalidomide, one enantiomer was effective in alleviating symptoms of morning sickness. The other enantiomer is actually teratogenic. This means causing birth defects. And so if you give people one enantiomer, it helps with seasickness, morning sickness. The other enantiomer causes mutation in the baby, possibly killing it. Okay? So the drug was initially sold as a 50-50 mixture of the enantiomers. Many mothers who took it then gave birth to babies with severe defects. And so why is this stuff important? Because it literally has life and death consequences. Okay? So right here we actually see a more benign, more fun example of this, which is carvone and carvone. So see, this is R carvone, this is S carvone. See the difference in the enantiomers? Okay. Okay, so S carvone is spearmint. Everybody smelled and tasted spearmint before, right? Okay. R carvone is caraway seed. So you know everybody had caraway seed before? No, it's not as popular of a flavoring by any stretch of the imagination. That tells you something about what it tastes like, right? Yeah. So Escargot spearmint, very popular flavoring. Completely different flavor are enantiomer. Okay. All right, so this is, again, some isomerism in organic compounds. Here we have the morning sickness drug right there, and the proper enantiomer, proper orientation. It's this bond right here is the chiral carbon. Okay? And this would be the other one right here. And so notice it's just on different sides of that ring, isn't it? Can everybody see it okay? So it's just a mirror image of each other and a different orientation, birth defects if you give it to a mother. Okay. All right, so this is your study guide for the chapter. Does anybody have any questions about this material? Okay. This is very much a sort of thing you have to practice on, okay? You're going to notice as you do the homework problems, you get a much better handle on these. Use your hands and objects around you to model these things in real life, okay? Like two-dimensional structures are a little hard to grasp, but if you start modeling them with your hands in a three-dimensional world, they're a lot easier, okay? And if you want, you can come in and I can loan you a kit, okay? You can actually make these structures. All right. Anybody have any questions at all? Wonderful organic structures, okay. We're going to go ahead and start up on chapter 5 now.